Formula. So we're looking at optimization problems. We did lots of these problems in grade 11 where we optimized or found the vertex of a parabola. But now we're just going to find these vertices using calculus. Okay, so these are how we're going to optimize these problems. So here the top of a projectile motion, there's a parabola going up and down. We can find the vertex of this using, our grade 11 math, but we're just now going to, instead of put it into graphing form, we're just going to differentiate. So if I want to find the max of that point, I'm going to differentiate that and solve for that derivative is equal to 0. So that's going to be t. So solving where that's going to be equal to 0, okay, we are going to end up with t is equal to 10t equals 5, so t is equal to 1/2. Okay, so when t is equal to 1/2, we have the maximum, so we can actually calculate the height as well. When t is equal to 1/2, we get 5 over 4 plus 5 over 2, which is 5 over 4 plus 2. So we're going to end up with 13 over 4. Okay, meters. I think this is going to be in meters. So find the maximum height of the projectile. We find out where the time is going to be the max, and then we just plug it back in to find the maximum height. So this is a problem that's not, if we forget how to do this, we can always just find the vertex here. For a problem like this, again is a grade 11 problem, we're trying to make a box using a piece of paper, and we're going to find the maximum volume of this box. Now in grade 11, we couldn't find the max of this cubic function because we're going to end up with a cubic function. So we would have had to use technology, but now we can apply calculus to this problem. So here, first things first, I need to come up with an expression for the volume here. Okay, so I'm going to call these little bits x I'm cutting out. Okay, if this is 30, we have so we'll look at this length here. We know that this length here, that edge is going to give us the edge of the box. So we're going to take away 2 x's from that edge. The height of the box is going to be x. So our volume is going to start looking like this. Okay, volume is equal to the height x times 20 minus 2x, which is a width. And then we just need to figure out this length here. The way I'm going to do that is, well, if I take a look at this length, here is going to be the middle where I split it through here. That means then that this length will be half of 30 or 15 minus just the 1x right there. Okay, so then that's going to be my other edge length. It's going to be 50 minus not 2x but 1x. Okay, so we are then, just make sure I got that right. Yeah, I've got my length here, my length. Okay, so then this volume, there's my volume formula. Okay, if I want to now differentiate, I want to find the largest volume of this, I just need to differentiate, find out where I'm going to have a max. So I really should multiply this out because it's going to be easier to multiply out or to differentiate when I multiply this out. So I'm going to end up with 300 minus 30 minus 20, so minus 50x plus 2x squared. Okay, so the volume is equal to 2x cubed minus 50x squared plus 300x. So I want to find the volume, the derivative, minus 100x plus 300. So I'm going to find the derivative. I want to then find the max point. I'm going to factor that. So v prime okay, so then that looks like what, two numbers. I'm going to just do this, multiply to 450 and add to 50. Oh, that's a tough one. I think that's going to be 450. I think I'm just going to plug that into the quadratic formula. I don't think that's factorable. So I'm going to solve for x. It's going to be 50 plus minus 2500 minus 4 times A times C. Okay, so, and that's going to be all over 6. So the largest volume, the x for the largest volume works out to be, that's going to be 4 times 150 is 600, times 3 is 1800. So I'm going to get square root 700 over 6. And that's going to be approximately equal to, I've got a calculator here, so I might as well use it. Okay, so I get 50 plus square root 700 divided by 6. And that's going to give me approximately 74. Okay, that looks not reasonable because if I cut off that much, I'm not going to have any edge here. So the other solution, so I'm just going to, that's extraneous for this problem anyways. So I'm going to subtract. Okay, so I'm going to end up with 3.92 centimeters. That looks like the right answer. Okay, so it says that's the x I'm going to cut. I still need to solve for the problem. So the volume of the largest box, if I plug it into my formula, okay, so I'm going to get 3.92 times 20 minus 2 times A, 2 times that, and then 15 minus 3.92. Okay, so I'm getting a volume, if I did this correctly, I'm getting a volume of 528.15. Okay, so volume is 528.15 cubic centimeters. That would give us, that is the largest volume that can be constructed from that piece of paper.